we present ForceSight, a text-conditioned, transformer-based robotic planer that enables coarse-to-fine visual servoing by proposing tactile and kinematic objectives. These objectives consist of 3D fingertip locations, grip force, and resultant force applied to the gripper, all of which comprise what we call visual force goals. By predicting visual force goals into the future, ForceSight enables a simple visual servoing algorithm to execute a variety of tasks. ForceSight is an RGBD-adapted, text-conditioned vision transformer that encodes an image from a gripper-mounted depth camera in order to predict visual force goals associated with the next step of a specified robotic task. These goals are represented in the camera frame, thus enabling image-based planning. This also makes our predictions agnostic to the camera mounting location. We also provide the network with sub-goals specific to the task by appending action primitives to the prompts, which we find improves performance. These sub-goals can be provided beforehand, or could plausibly be generated by a large language model. These sub-goals are updated by the low-level controller when the robot is close to the current goal. We trained ForceSight by collecting pairs of hand-specified keyframes, where we learn a mapping from a text prompt and an RGBD image to a visual force goal. We pair keyframes together in a many-to-one fashion, where multiple initial states are labeled with the correct goal state. Additionally, we include items relevant to many of our tasks in each keyframe. This allows us to map many initial frames to a single final frame for each task. By reusing keyframes for multiple time steps and tasks, we perform data collection 5 times more efficiently than if they had been gathered sequentially. See the following examples of tasks performed by a simple low-level controller enabled by ForceSight. Our low-level controller uses an error metric that is a linear combination of the translation and force errors. When this heuristic is below a specified threshold, the low-level controller increments the sub-goal, which is appended to the text prompt. We find that ForceSight successfully executes all of our chosen tasks, and outperforms our baseline, perceiver actor. We also observe that ForceSight has multiple emergent properties. Aside from being agnostic to the camera perspective, we find that ForceSight generalizes to unseen environments and object instances. We also show initial results demonstrating that tasks performed by ForceSight can be composed to accomplish longer horizon tasks. Although ForceSight exhibits encouraging performance across diverse and challenging tasks, we recognize certain limitations and areas for future improvement. Our most common failure mode was error in predicting the depth dimension of the visual force goals. We think that these failures are due to our representation of depth as well as noisy depth measurements. Secondly, our range of tasks is quite limited and includes mostly pick and place. Given the inherent scalability of transformer models and the efficiency of our data collection procedure, we are optimistic that our methodology could be expanded to a much broader range of complex tasks in the future.